Okay, so we're finally getting to quantum mechanics. We're going to start talking about the quantum mechanical model. So this is something that was developed by Schrodinger, and again, it came out of the Bohr model, and then them understanding that the good part about the Bohr model was he figured out that there are specific energy levels. The part that didn't work was there was no way to really know with certainty where the electron was and where it's headed at the same time. So in order to figure out where an electron is, and this is what we have to do with a lot of our experimental evidence, is you have to do something to it in order to see it. So the process of like hitting an electron with something so we can identify where it is, we're like pushing it. So in order to know the position and the momentum or velocity at the same time, there's a certain amount of error associated with what we're doing experimentally. So that is the Heisenberg uncertainty principle. That's in the slide. I'm not going to write it up here. So because of all that, he was able to come up with this quantum mechanical model. So you'll see in the reading there's a lot of wave equation, wave functions, and all of that is because he focused on the wave-like part of the picture of what an electron is, or what an electron's doing. So the wave functions, we won't use that word a lot. The word we'll use a lot is orbitals. And orbitals actually come from, turn that off. Orbitals come from what you saw before in the Bohr model, so we know they don't work, they don't go in orbits, but the word orbitals historically came from that. And the other thing that historically came from Bohr was this N designation, which was given the energy levels. So these orbitals aren't in particular locations and going in a certain way. All we can say is where the electron probably is. So there's this three-dimensional space where there's a high probability of the electron existing. So it's really hard to conceptualize that we don't know where something is, but that's one of the limitations of the model that we have. And there's other models, but this is the one that's kind of accepted. In order to describe this three-dimensional probability space, they have what's called quantum numbers, which goes along with the quantum mechanics. And these are variables to describe things like the distance of that three-dimensional shape, or the average distance of an electron from the nucleus, which is important because we want to know which ones are on the outside, because those are the ones that are important in bonding. We call those a shell. So we'll talk about in a little more detail in the next part that I do. And then L, when you see that designation, and this is on the Alex homework, it's the shape of the orbital. So there's like the S shape, the P shape, the D shape, the S or the F shape. Those are called subshells. So I may use that designation. The last one that we'll talk about is this M sub L, this little M sub L. This is a magnetic quantum number. So that's the number of orbitals. So this is where the electrons have to exist in a way that they aren't interfering with each other. So 2 electrons can fit in each one of these orbitals, and we'll talk about why in a second. So to continue with the quantum numbers, again, the quantum numbers are describing, we don't know where the electrons are, we know where they probably are. So they're describing this space where the electrons have a probability of being. So of these 3 numbers that I have here, we have the principal quantum number. The principal quantum number describes the average distance from the nucleus, so how far away the electrons are. And this is, because it's the average distance, it's really how far they are relative to each other. And the energy level. So the further an electron is from the nucleus, the higher energy electron that is. So like n equals 1 would be here, n equals 2 would be some space here, n equals 3 would be some space here. And then the L value is called the angular momentum quantum number. The important part about the L value is it describes the three-dimensional shape. So you'll see those when you do the ALEKS homework. Some of them are spheres, some of them are like these two like lobe looking things, some of them look really weird. But it's a three-dimensional shape where the electron has a probability of being. So it's somewhere within that particular shape. These L values depend on what principal quantum number you're in. So the L values depend on how far you are from the nucleus, the allowable L values, the allowable shapes. The last one is the magnetic quantum number, and what's important about the magnetic quantum number is it gives the number of orbitals. And the orbitals are where we talk about a certain number of electrons being able to exist. So it's a certain number of orbitals for each subshell, and remember subshell is what we're calling the L. And then there's 2 electrons max that can exist in each one of these orbitals. We're going to talk more about orbitals when we start writing out the electron configurations, but this gives you a summary of what the quantum numbers are. And then the other thing I want to do is give you some examples that would be in the homework so you can see what they're referring to. So when we write these out, when we write like the N and the L out, we'll have some designation like it'll say 5D. So when it's saying this, or it'll say 3S, it's telling you the N. So this letter, or sorry, this number is always the N value. So that's N equals 5, N equals 3. This letter designation is the L. So this is a particular L value. This is a particular L value. So the L's are the shapes and they have these letter designations, but because there's a mathematical relationship that's used to relate the L to the N, we have to also give them a number. So let's just write over here in the corner, and there's a really good slide that I'll tell you about. So for the L values, there's the shapes. So we have our letters. So L can start with 0. It can go beyond 3, but not for our periodic table. So if L equals 0, that's an S. If L equals 1, that's a P. If L equals 2, that's a D. And if L equals 3, that's an F. So on the ALEKS, if it asks you, like if they give you that designation, if they say 5D, that means L equals 2. If they say 3S, the L's coming from that letter designation. For an S, that's L equals 0. So the table that I want you to look at is table 5.2. It tells you all the possibilities for the L, the N, and the M sub L related to each other. There's no designation here for the M sub L, but it's in that chart. Let me make sure I got the right. Yes, so that's in the book, but it's also in the slides, just in case you don't want to look for it in the book. Last thing, really quick, is the shapes, because you have to do the shapes on ALEKS, but it shows you the shapes in the ALEKS. Anytime you have an S, it's going to look like a sphere. anytime you have a P, in the book it looks different in the Alex, but they're kind of designating the same